Good evening, sir.
Hello. Good evening, Rishabh.
Yes, sir.
Okay, so we'll start. Others joined.
Yes, sir.
Okay, so we're going to show the uniqueness of the okay, so this problem. So okay, is it okay? Can you see? I'll just show you what we have done last class, and then now we show the uniqueness so that you know how to calculate that UZ. Okay, so let's do it from here. Mm. Can you see this one? Where is it? Okay, here. Okay, so here, yeah. You can see, right? What's going on?
Yes, sir.
Lecture 38, as you see, NL equation, that NS equation we have considered. This is corresponds to steady viscous flow through a tube with arbitrary cross section. Steady, this becomes 0. Left hand side is this 0. So left hand side we have shown this 0. Then Navier-Stokes becomes this one. And you basically, once you equate these coefficients, P is only function of Z. So function of Z, and this is only function of right hand side is the function of X and Y, UZ. Okay. UZ is anyway function of X and Y, no? So this has to be, it's moving towards the Z direction, so it has to be minus, this is the negative derivative of this P is negative, so it is minus P naught, where P naught is positive. So now we are looking at, we are going to solve this UZ. So we just look at this one. So whatever we are doing, so this Laplace equation, how do we show that Laplace equation? With right hand side something, and on the boundary, where is this boundary? XY. This is like this is your closed boundary. This is your domain. Okay. So whatever you are seeing now, that circular round thing, arbitrary domain, that is your boundary. Inside is basically you have Laplace equation is satisfied. With right hand side is something. Okay. And on the boundary, the value of the unknown. So the function UZ is 0. That is no slip condition. So that's what we need to show, that such a problem has a unique solution. So uniqueness theorem, that's we called uniqueness theorem. Okay, so now I stop sharing this one so that can you see mine? Yeah, uniqueness theorem. For Laplace equation. So what it says is you have some arbitrary cross section. Okay, this is, you call it omega. In this you have del square phi equal to 0. Okay, so del square phi is 0. Let us call this phi. Okay, so what its theorem tells you that the problem, boundary value problem, del square phi equal to 0, where xy belongs to omega, this one, and phi is actually equal to 0. So I'm not taking any, you can actually take any constant, still it is the same, any function. Okay, phi of xy, phi on this boundary dou omega. So this is your dou omega. On this is actually given 0, but you can also take it as some function of xy. Okay, so this function, this has the boundary value problem. as a unique solution, So how do we show this one? So let's give the proof. It's a simple proof. So we consider that Gauss divergence theorem. So divergence theorem tells you what is the divergence theorem you have. So you'll have an integral over. So okay, see what we do. Divergence theorem. Let's consider this need not be even R2, no? So what is the divergence theorem in R2? Same thing, no?
Sir.
Isn't it? Hello?
Yes, sir. Yes, sir.
Can you see divergence theorem? Is there anything, something called the divergence theorem in 2 dimensions?
But how we can integrate, sir, in 3D, like convert from del omega to
See, 2D divergence theorem, let's look at what it is, what it tells you. See, you're not doing anything. That I think we call Green's theorem, right? Yeah, f dot n divergence of f over r. Yeah, the same. You see, instead of triple integral, you are going to write double integral, and here it's anyway cosine. So there, divergence theorem. What do you put there? You have a surface integral. Surface integral become here. It's what is that one? Line integral. Okay. So in 2 dimensions, so what it says is 2 dimensions. So you have a double integral over omega. Okay. Del dot f equal d dA, okay, dx dy, because they were in 2 dimensions. This is part of R2. Okay. So this is equal to integral over always in the positive orientation. So this is the one. Okay. So when you take like this, the normal should be outward normal is this one. So n cap. So you have to go in this direction so that you have you on your left hand side should be your domain. If you are walking along this path, left hand side should be your domain. So then the outward normal is in this direction, so on the right hand side. So this is over C on the, this is anyway closed curve, not over C, the delta omega. Okay. Then what is that? So f bar dot n cap d. What is that you do here? ds. This is your simply
yes, sir.
line integral. So this is what you have. Okay. So now let's now take any question up to here?
No, sir.
Any question up to here?
No, sir. No.
Okay. So now what we do is we'll try to let I take f bar as a phi into grad phi. It's a vector field, right? Then integral over omega del dot of phi grad phi dA equal to integral over delta omega. F is phi into del phi dot n cap ds. Okay, that's just a line integral. dl also you can take it. Okay, so what is this one? This is actually nothing but dou omega into phi into, what is this gradient? Gradient dot n product is dou phi by dou n, right? Dou phi
Yes,
by
sir.
dou n
Yes, sir.
ds. What happens on the left hand side? So left hand side it becomes
Sir,
del dot phi. Yeah, what it becomes here? So
yeah,
this I can say del phi dot del phi. So integral
del P square.
del phi square dA over omega plus double integral over omega. What else you have? Phi
Phi.
into del dot del phi. So that is phi into del square phi into dA. Okay, followed. But this is 0. So del square phi is given as not 0, right? So it's not 0 for you. It is given as something else. Yeah, this is okay. So okay. So what you need to have is, I think we can also take it here as some f. Okay. So it is not f. So now this is what we use now, right now. So this inequality, you call it star. We use this one. So let phi1 of xy and phi2 of xy be two solutions. Standard procedure to show the uniqueness. Okay, define phi as phi or w, we call it w of x equal to xy equal to phi1 of xy minus phi2 of xy. Then what happens? Del square w is equal to del square phi1, because there are two solutions, right? Del square phi1 minus del square phi2. What is del square phi1? Two solutions of the boundary value problem. That's what we mean, right? So equal to what happens? There the boundary. This is our boundary value problem. So that is del square phi equal to f. So here you have two solutions, no? F minus f, which is equal to 0. That is in omega. So what happens on the boundary? W equal to phi1 minus phi2. This is 0 minus 0 is 0 on dou omega. On the boundary, phi1 is 0. On the boundary, phi2 is also 0, right? Because it satisfies the boundary condition here. Boundary value problem. Okay? Any questions up to here? I can go ahead, right? So now you apply this, apply star to W function to get integral over omega del W whole square dA plus integral over omega phi into, not phi, W into del square W dA equal to here dou omega W into dou W by dou N into ds. Right? So now you know that the del square U is 0 in omega. So and W equal to 0 on dou omega. So right hand side is 0. So this implies this grad W square dA. This whole thing is 0. This integral is 0. So you'll have equal to 0. So this implies means what? Some positive quantity over dA or omega is 0 means del omega has to be 0. Isn't it?
Yes, sir.
What is the meaning of that? W is constant. That means W equal to constant. Constant in omega. And we know that W is actually equal to 0 on dou omega. By continuity argument, it has to be 0, right? So that means that constant has to be 0, right? Because it is satisfying inside Laplace equation, and then on the boundary it is continuous. W is continuous. W of xy is continuous in omega and on delta omega. That is omega bar. Okay, since this one,
So if Wxy is a constant, then it means any fixed number. So it is already continuous everywhere.
huh?
So if Wxy is equal to constant, we got that
Hmm.
means Wxy equal to any scalar number, any scalar.
Yeah, but on the boundary it is 0, no? You already know that it is 0 on the boundary.
Yes, sir.
So that is why for this to continuous, this constant has to be 0.
Okay, sir.
Fine, right? So this is true for every xy belongs to omega union delta omega. Okay. So what is W? Phi1 equal to phi2. That implies uniqueness for the boundary value problem. Okay. you replace Robin condition. So even if you replace Robin condition, you will get the same similar proof. Okay, so this is the uniqueness proof for fluid mechanics point of view. So you have the boundary condition is only this one. So now you go back, and if you see, go back to your problem that you have. So I'll show you now what we have on the last class. Yeah, so this is your problem now, right? So this has a unique solution, right? Now what is its solution now? Whatever you are seeing, right? So I need to write the problem now. So minus, so I am writing, so getting back to the, so implies minus P naught equal to dpz of by dz equal to mu times. You have dou square uz of xy, function of xy by dou x square.
Please present your
Huh?
so please present your written notes, sir, like whatever you are writing. We seen previous notes, sir, we are seeing.
Previous notes only I'm saying. I'm saying, okay. I'm just rewriting. I'm just bringing it to you. So back, okay. So I'm stop sharing here. So now you can see what I have. Okay. So this is what we need to see. Okay. Now you consider this equation. So what is its solution? So what is the solution that you have? Dou square, or I'll simply put it like del square uz equal to minus P naught by mu. Where? Inside? Now you can consider no arbitrary cross section that you have, right? So that cross section is arbitrary. Arbitrary tube cross section. Okay. Now case 1. Let the cross section be ellipse. So what is the cross section? Then x square by a square plus y square by b square equal to 1, isn't it? That is the ellipse, right? So your curve is basically this one. Sorry, your curve is arbitrary cross section becomes ellipse. Okay. This is your A, B, or whatever you say, so doesn't matter. Okay, so this is your ellipse. So this is your omega. Omega is in dou omega is basically that we call dou omega. Okay, so dou omega ellipse is basically dou omega. Okay. Now, what is the solution now for this? I am just looking for my solution uz of xy and such. Okay. Just assume like this. Just look for one solution like this. This uz unknown, I am looking for solution as 1 minus x square by a square minus y square by b square. Now, if your xy is on the ellipse, then automatically this is 0, right? Of course, you have a boundary condition. uz is
Yes, sir.
0 on dou omega. Okay. So this into some number k you put it, where k is unknown, where k is a constant. Then you substitute into the equation. So if you substitute into the equation, what happens? K into, with respect to x, if you differentiate twice, I will get minus 2 times x divided 2 by a square. Similarly, you have minus k 2 divided by b square. I differentiated twice this equation, this uz equal to minus p0 by mu. So p0 by mu is anyway constant, right? So this give me what is my k? K equal to p0 divided by mu times what else? What you can do? Divide by 2 mu. You can 2 also you can divide, and then you have b square plus a square right? Divide by a square b square. That's what is your k. So just go and substitute. So since by uniqueness theorem, uz of xy equal to k you write it as p naught into b square plus a square divided by 2 mu a square b square into 1 minus x square by a square minus y square by b square.
So there should be reverse, sir.
Is the solution.
Sir, k equal to, I got p naught a square b square divided by 2 mu a square plus b square. There should be reverse, sir.
A square b square. Oh yeah. Okay, sorry. A square b square divided by a square plus b square. Right? Yeah. A square b square divided by a square plus b square. Okay, that's fine. A square b square divided by a square plus b square. 2 is fine, right? Yeah. So this is your this is the solution. Okay. So this is the solution. So once you know the solution, you can get your pz. Okay. Pz you can differentiate. Followed?
Yes, sir.
Yeah. This is the way you have to calculate. Okay. So we basically solve the PDE satisfying the boundary condition, that is a unique solution. So that's how you get your solution. Okay. So let's see what else we can do. Once you get this W, you can actually get your P also. Okay. P you can calculate and see. But we will not do anything. So what is that flux through this elliptic kind of tube? What is that amount of fluid implies? I'm just giving the just the formula that you have. Amount of fluid. What is the fluid? Amount of fluid through the elliptic tube per unit time. What is that one? It is equal to, it's a flux, right? So basically it's over that omega, this whatever u z of xy d surface. Okay. So what do I do here? What is that I have to do? This integral over dou omega, right? It's over dou omega, double integral, surface integral over dou omega. Is that yeah, what is that you do? What is that you have? So this is a cross section you have. So this is the dou omega. Dou omega is basically, that is over omega, right? Not dou
Yes,
omega.
sir.
It should be over omega.
Yes,
Double integral. So that you have a double integral. Okay. So double integral. I think this is simply surface. Right? You consider over the surface.
dA.
dA. Okay. So let me write it as dA. So I think this dx dy only. Okay. Dx dy. So this is what you need to calculate. This is the flux that you can easily calculate, knowing what is this one. So this is the integral you will have to evaluate. Dx dy. Okay. Shall I leave it here? So that is the case 1. So case 2. So let's look at the case 2. What is the case 2? What is arbitrary cross section? Now I can take it as, so when omega equal to a triangle with equilateral, with same sides, with equal sides. So to do this, we'll just try to do the way it is done there. You can do many ways. I'm trying to follow x equal to a. X equal to a is this line. Okay, this is one line. And you have y square minus y square equal to y square minus x square. So you'll have 1 by 3 times x square equal to 0. So those are these lines. These are these lines, right? So where is this cutting? X equal to a, if you put it, what is your y? Y equal to plus or minus 1 by root 3
A square by 3.
a square, right?
Yes.
A, basically a. So this is the point a comma a by root 3. This is the point a comma minus a by root 3, and this is the point 0 0, right? Passing through 0 0, right? So this is your basically your region. This is the equilateral triangle. You can observe that a minus a square plus
Sir,
a.
why do you will select this equation? So y square minus 1 by 3x square equal to
This
0.
is one way. You need not do. So you can the way you like. You can do the way you like.
Okay.
I can also do. I can start with the bottom being like that. Take one line like that. Some linear equations. You take it. You can do it the way you like. This
Okay.
is one way.
Okay. Sir.
Okay. This is one way. Simply see by this way. What I do is my equation. So my thing is that see if what is that you want on the boundary you want, no? If I write like x minus a into y square minus x square by 3. This I can say that this is actually dou omega equal to 0. Okay. This is the boundary, right? If you actually see x equal to a, all the values are at x equal to 0, it is 0. Isn't it? Yeah. So what is this one? This is actually y equal to some constant times x. This is equal to minus constant times x. This line, whole line. So it satisfies automatically. So it is actually 0 on dou omega. This is equal to 0. So it is automatically satisfied. I am looking for u z of xy. Now for the problem in this cross section, for this triangular cross section, omega is this sides. In this case, u z y, I call it ansatz. Okay. Ansatz is some constant times x minus a into y square minus x square by 3. This is not the only way. Okay, if I try to do my way, then I'll have to do calculation. So I will only lose the time. So you can try the way you like. It's all same.
Okay, sir. Okay, sir.
Okay, so you do. I'm just trying to imitate what they have. So this is the one. This you substitute into the equation. So that equation, if you try to do, what is that one? What do you get? Minus p naught divided by mu equal to, you differentiate with respect to x. Twice if you do, it is 0, right? That is 0. What happens? The y square, if you do a into 2 only, right? Oh, no. I think we should get something else, no? So what is x? X, if you differentiate twice, only get. Just give me what is the differentiation? X minus a into y square, that is 0. So I'll have a minus k. Okay, minus k into x cube, right? Minus x cube by 3. And then what else you have? Plus ax square by 3. So this is what you have. So into minus k, right? This if you differentiate, you understand? X minus a into y square, if you do twice integration with respect to x, that is 0. And then what is the other term? Other term is minus k into x square minus x square by 3. I am multiplying with, x square by 3, I multiply with x minus a. That is what will happen. Correct? I think I made a mistake. I think this is the minus here, isn't it? Yeah. So minus 3x square minus 6 minus 6x by 3 plus 2a by 3. Is this correct? Hello? Yeah, you'll see this one. Okay, that is what is this first one. dou square uz by dou x square is this term. Now plus dou square uz by dou y square. If you do, what is that you will get? Y square if you do 2k into x minus a. That's all, right? Whatever the other terms are, simply 0. Partial derivative with respect to y is only gives you basically 2 times x minus a into k. So this is what is this one. So 2kx, this is also 2kx. Okay, minus 2ks plus 2kx gets cancelled. So what you have is minus p0 by mu equal to minus 2kx plus 2ka by 3 plus 2kx minus 2ka. So this gets cancelled. So what you get is 2ka times 1 by 3 minus 1 minus 2 by 3, right? So we'll have minus 4 by 3 ka. You get the same number, Rishabh?
Sir, yes, sir. First part I got same, sir.
Yeah, okay. So minus minus cancel both sides. So I will have k equal to, now I can get it from this. I can get k equal to 3 by 4 a mu into p naught. So go and substitute. So this will give me now finally what is my uz of xy. Uz of xy equal to k is now 3 p naught by 4 a mu times x minus a into y square minus x square by 3. So this is what is your function. Okay. So in the case of horizontal cross section, yeah, 3 by 4 mu. Yeah, I have also got the same number. Yeah, that's okay. So this is what it is. Okay. So with this, I think I will close this chapter. Okay. So this is the one that says the steady viscous flow in uniform arbitrary cross section, and particular cases are like elliptic and triangle region that I have taken. So we can actually calculate use that. So implies what is the next step? We can actually get this no amount of fluid through this elliptic thing. You calculate this one similar.
Just we can integrate, sir. What
Yeah,
is
just
the sir, boundary condition we will put omega, sir, like x range and y range, sir.
x minus a into this one.
In for calculating flux, sir, I am asking for. Then we can put like x is 0 to a and
Yeah. Yourself. Okay. So
Okay.
the amount of fluid discharged through the pipe. I mean this triangular pipe in unit time. Integral over this triangle. So over this triangle, this uz of xy dx dy. So when you do this, you try to convert this into, you have something like this, right? So I have 0 to a. So integral from 0 to a dx first. Now this is what is this line or what is this line? This line is y equal to 1 by 3x. 1 by root 3, right?
Yes, sir.
This line is y equal to, minus 1 by 3, 1 by root 3 x.
Sir.
So that will be my dy. So dy, once you fix x, you're going from here to here. So that is y is going from, x is going from this, y is going from minus 1 by root 3 x to plus root 3, 1 by root 3 x. That is your dy. So now whatever you have, you put it inside now. So uz of xy. You calculate this one, this is finally going to be number. So that is what is this, unit time is q. Okay, this you can do your calculations, whatever. Okay, so you take it as an exercise. So that is what I leave it here. Okay, so this section is done. Any questions up to here? How many are there, by the way? So 9 plus 9 minus 3, 6 are there. 1, 2, 3, 4, 5. Joe is around. Okay. Joe, how are you? Are you following? Okay, so what shall we do now? Now we need to do the only thing that is left. The only thing that is left is flow past, viscous flow past. Sphere. We'll do for sphere. Okay. Cylinder also you can do, but I'm trying to do only for sphere. Okay, so we are going to use spherical coordinates here. So before we do this one, so what we do is, before we do this, we're going to take the Navier-Stokes equation. So what is the Navier-Stokes equation? So Navier-Stokes equation is, you write what is the Navier-Stokes equation? Dou U bar NS equation. We non-dimensionalize this one first. So dou T plus U dot grad of U equal to minus grad P by rho plus or minus. It's minus, right?
One plus, second one plus.
No, that is plus mu times mu by rho, right? Mu by rho del square U. So this is what is your Navier-Stokes equation. We try to, this is the dimensional form. Dimensional. Okay. It's a dimensional form. So how do I non-dimensionalize? I want non-dimensionalization. Non-dimensionalization. You know how to do non-dimensionalization? Have you done any time? Hello?
No, sir.
Okay, see, we're going to use the sphere of radius A, for example. Okay. So if flow past sphere means you have a sphere, some sphere you have. So sphere of radius A. Okay. There is a structure whose length is A, right? So typically in your problem there should be some characteristic length should be there. Okay. So we use the scales. Using the scales, new variable. So what do you have? X, Y, Z you have, right? So I'm trying to use X bar. X is the vector, right? So capital X we use, right? So let's say capital X. Capital X. I'm just trying to use only simple variables. Okay. So let me write it as X bar. X bar has my X, Y, Z. Okay. So X, Y, Z. Okay. So then the scales, or let us say where I'll write where. Okay. So what are the scales that I use? X bar. This dashes equal to X bar by L. L is the typical characteristic length. And then you have U bar dash equal to U bar divided by some uniform flow that you have involving, no? At infinity, you have a uniform flow with some velocity U. So typical velocity you give, this is the U. Okay. With that, this is your characteristic velocity. Okay. And then we try to use the time is also there. So you'll have a time T dash equal to T divided by some fixed time. These are called characteristic, basically characteristic time. So where X is this, L is LUT or characteristic length, velocity, comma, time respectively. Any question up to here?
No, sir.
Now just try to do. Now try to use these scales. These are kind of you see it as a transformation and put it back into those u. Okay, into your. So what happens if you have this one u bar? Now what you want is u bar is actually u into u dash, right? So this u numerator u bar equal to u bar dash into or u dash bar. Okay, so you try to make it as u dash bar.